for you.
Okay.
Can you see my screen?
Yes.
Okay.
Can you hear me?
Yes,
Yes.
again.
Cool. Yeah. So let's get started. So hi everyone, I'm Hideto, engineer from SiFive, and today I and Prithayan are going to talk about the next generation Firtool compiler, which we are working on almost 2 years. And next slide, please. So last year we presented our motivation for why we had to rebuild the compiler. Right, our major problem of Scala-based Firtool compiler is the performance. I think it is very common that it takes hours to compile large designs, and it also consumes a lot of memory, like over 64 gigabytes, and it makes it very difficult to compile large design on the a normal laptop or normal PC. So another problem is that it is difficult to extend the language of Firtool because of the infrastructure reason. I mean, for example, it's very hard to add parameterization stuff or custom node IR to introduce verification contract. So to address these issues, we started to create a new Firtool compiler with MLIR. Next slide, please. So today we have the next generation Firtool compiler called Firtool, aka MFC, MLIR-based Firtool compiler. So this is already used in production flow at SiFive, and so Firtool is a drop-in replacement of SFC. So Firtool takes file and annotation as input and passes files into Firtool MLIR direct. After translating into MLIR direct, we apply a lot of passes on Firtool level, like lowering types, and also applying a lot of optimizations or checkers. And eventually, they will be lowered into circuit core direct, such as system Verilog direct or hardware direct or combo direct. So after lowering circuit core direct, we can benefit from the power of the infrastructure. I mean, there are also a lot of optimization in core direct, and also there is a good mechanism to emit a good system Verilog. And regarding performance, MFC is faster than SFC, like 5 times, 10 times faster than SFC. So because MLIR is very efficient, and also it has great parallelism support for IR. So that's why it is very, MFC is very fast. So I talked a bit about the circuit. So here, let me talk more precisely about the circuit in detail. So please next slide. So here, circuit is a project to create an infrastructure for hardware description language. So the goal of the circuit is to become the foundational technology, which is very similar to what LLVM did for software compilers. And the circuit already has a bunch of composable toolchains, very useful toolchain, like you can see on the right here. It shows the toolchain dependency of circuit, and I marked their Firtool pipeline as red. And it means that there are a lot of interesting work other than Firtool, like their PyCD, Moore, or FSM or System C. So maybe if you want to use these kind of stuff, it might be a very great opportunity to contribute to circuit. Next slide, please.
Thanks, Hideto. So in this slide, we're just going to show a snippet of what the internal IR circuit looks like. So this is showing the FIRRTL dialect. So as Hideto mentioned, there are several dialects in the MLIR compiler. So this FIRRTL dialect, it's showing how we represent the different operations of the FIRRTL in the in our IR. So for example, there is a circuit node, then there is a FIRRTL.module, and inside that we have IR operations for each of the constructs in the FIRRTL. For example, the FIRRTL.add and FIRRTL.node. So we can use the binary called Firtool to parse a FIR file and then generate this FIRRTL dial. Here we are showing the pipeline of the different passes that is run when we take a FIR file as input, and the output could be the Verilog, or we can also emit different JSON files as the metadata, or even text files, or even the IP exact. So the output can be a lot of the different things that is required for the project. So as we mentioned, there are different dialects in the compiler. So the FIR file is parsed into the FIRRTL dialect, which has these various passes. So we'll not go into details of all the passes, but in the next few slides we'll discuss some interesting passes that we have in the FIRRTL dialect. So in the compiler, different dialects can coexist. So for example, the FIRRTL dialect can generate some constructs from the hardware or the SV dialect, and then finally the FIRRTL dialect is lowered into the hardware and the COMB or the SV dialects, and then there are different transformations on the SV dialect, and then finally the export Verilog generates the Verilog files from it. So let's dive into some interesting transformations in the in our pipeline. So here we are going to show the full async reset transformation, which is implemented in the FIRRTL pipeline. So what this transformation does is that it infers the reset domains associated with each module based on certain annotations that the user has provided, and then it will find out all the registers which don't have an async reset signal. So it will associate the user marked reset signal and then use it to initialize the register to 0 with that async reset signal. So for example, here without the async reset transformation, if we generate, then the last grant register is not initialized here on the top right hand corner. But if we run the full async reset transformation, then we can see that the signal X, which was marked with the annotation full async reset annotation, is being used as a async reset signal, and then the register is being initialized to 0 based on the async reset. So right now this this annotation is internal. It's not yet exposed to the chisel, but the transformation is implemented, and it should be simple to expose this to the chisel API if it's interesting. And I have mentioned the path of the FIRRTL transformation in the MLIR repository. So the next interesting transformation that we can look at is the called Flatten Memory. So here what it does is that given any memory with aggregate data type, it transforms the memory into an unsigned int with the same width as the aggregate type. So it replaces the aggregate data of the memory with a uint of width which is equal to the sum of the individual leaf elements of the aggregate. And what is interesting is how do you calculate the mask, because given this aggregate data type here on the top right hand corner, there is 3 elements here: ID, ENQ, and other. So the mask will also have just 3 bits to guard these 3 fields. So now the interesting thing is, given these 3 masks, we use concatenation to generate the mask for the entire flattened memory. We basically use the GCD of the individual leaf bits to figure out how many bits each of the mask bits should guard. So for example, here the GCD is 2, so each mask bit guards 2 bits of the final data, and then we concatenate the input mask widths to generate the mask width for this memory. So this pass is implemented in the Flatten Memory transformation in the FIRRTL dialect. Another interesting transformation that we have is the extract test code. So the extract test code has an analysis which takes all the simulation constructs like the assert, assume, or cover, and then it extracts them into its own submodule, and then all the data flow associated with that is also extracted into the submodule, and then these modules are then the separate modules are then instantiated in the original module. We can specify like output directories and different files for each of the simulation constructs, so that the assumes and the covers, all of them are extracted into their own directory. Hideto, you can take over from here.
Thanks, Prithayan. And here we'd like to talk about the recent Verilog quality improvement implemented in MFC. So one interesting thing is an optimization flag. I mean, this is very similar to the optimization flag of Clang or GCC in the normal compiler. This flag was created to deal with trade-off between the performance and the debugability. So let's see an example. So in the module foo, there are node D and E, and let's assume that these nodes are created by chisel variable. And for production build, we obviously want to eliminate these nodes because these nodes are unnecessary. And as you can see there in the bottom, in the release mode, these nodes are optimized away, and it provides as a better performance. But on the other hand, like it sometimes makes difficult to debug their output Verilog. And so in the debug mode, that's why we wanted to create the debug mode. I mean, in the debug mode, these T0 level variable like node or wire or registers are appearing in the output Verilog. So it makes us easier to debug their output Verilog. So next slide, please. So another fancy feature we are working head on is aggregate preservation. So it's very simple, right? We want to lower Firtool bundle and vectors into Verilog struct and arrays. And actually it is still ongoing, and not production ready yet, but we are working hard to make this aggregate preservation production quality. For example, in the module foo, there are input-output, which have their types of bundle and array. And by default, MFC compiles the module into the Verilog shown on the right. I mean, there are hundreds of lines of module port definitions because we are decomposing their aggregate into individual scalars. So also there are hundreds of lines of assignment because their assignments will also be rolled into their individual connection. But if we enable their aggregate preservation, then the module will become 3 lines of code. I mean, there are struct definition in their port definition, and also the connections are performed in their aggregate level. Like there is only 1 line of assign. So next slide, please. So from here, we'd like to talk about the future Firtool improvement currently working on. And one interesting ongoing work is subword assignment. And subword assignment allows us to use the bit index operator as the sink of connections. In this example, output out is assigned with subword assignment. In the first line, their bit between the 0 to 1 are assigned by constant, and there are one statement. In that one statement, there is the some other element, and as you can see it is very makes a lot easier to update the bit, and we will planning to provide Chisel API to to use these features from Chisel side. So Prithayan, please go next slide.
So this is another future FIRRTL improvement, which this is mostly an improvement in the infrastructure for the circuit compiler. We have introduced a new type called the reference type, and this is being used to represent cross-module references as explicit data flow. So these ref types would be basically removed during lowering and replaced by XMRs in the verbatim. So for example, on the left-hand side, it's an MLIR representation. So the details of this is not important, but we have a FIRRTL.ref.send, and then we have a FIRRTL.ref.resolve, and the data is passed through the module ports of ref type. So the send basically represents an input port of DUT, and then the resolve is being used to assign into a wire. So what the compiler lowers this is the XMR DUT.A, and then the DUT.A is being assigned to the wire GC_XMR. So this is a very powerful representation which can be used to express the like cross-module references as explicit data flow inside the compiler, instead of using like symbols or just strings to represent the XMRs. And like this can be verified, and like this has a lot of interesting use cases. Right now, this is not yet exposed to the Chisel API, but we are planning to expose this to be used by the Chisel directly. So this is the migration plan. We are in this presentation, we were mostly showing the capabilities that we have in the MLIR compiler, and so right now the Chisel circuit is already merged. So the Firtool compiler is available. It's also available as a binary distribution, which can be downloaded from this link here. But there are still some features which are not yet supported by the MLIR compiler. Some of the examples are like, for example, the fixed point types. The boarding utils is not yet supported, like injecting aspects, the enum annotations, and like these are some of the annotations which are not yet implemented in our compiler yet. So finally, we are committed to the Chisel's and FIRRTL's success, and what CIRCT enables is that it's a very powerful compiler, and it makes developing transformations and improving it much easier. So we definitely want more contributors, and if you start using it, please report any issues or bugs or improvements that you want on the on our GitHub. So here is a link to the GitHub. We have a LLVM discourse group where we discuss the different improvements to the MLIR. There is a Discord server, and we also have weekly meetings which you can join. So like, thanks a lot to all the circuit contributors. So there's a huge list of contributors which we have helped develop this. So yeah, thank you. That's all from us.